Seriously. Well, anyway, good afternoon. I hope you are doing well. We get to start focusing more on some characteristics of how vector fields work. So our goals today are, again, 15.2, talking about some characteristics of vector fields, how they behave, and then we'll start getting into the calculus in 15.3. So two things we're going to talk about today in this section. We're going to discuss what divergence and curl mean. How those work in vector fields, exactly what they mean. So curl does not mean this, all right? Yeah, very good. Divergence and curl, they're two characteristics that describe something about a vector field. Now, in order to describe this something, here's what I want to imagine. Imagine a vector field, which we pictured last time in 15.1. Imagine that this vector field describes how fluid or the flow of electricity, or some sort of substance is flowing across the field. Can you imagine that for me? So if you think of just kind of like the surface of a pond, that would sort of represent wind across it, that would represent the flow of that surface of the pond. So that vector field, the wind, could be very much a vector field, or even a 3D vector field. That's what I want you to think of vector fields as, is describing the flow of some substance across the field, and now that you understand the concept. Divergence and curl are two ways that we can describe that flow at a point, a very small neighborhood around a given point. So again, there are two characteristics. Now what do they mean? Well, if vector fields are describing the flow of some fluid across the vector field, then what divergence does, it's a measurement of how much fluid or flow enters a small neighborhood around a point compared to how much leaves it. That's what goes right there. So a measurement of how much fluid or flow enters the neighborhood around a point. Remember, this is all point specific. We're talking about what's happening at a specific point. Is fluid entering? Is fluid leaving? How much is entering compared to how much is leaving that neighborhood around the point? And now you can kind of picture that. So we're going to talk about that. If this fluid is moving, if the vector field is describing how the fluid is moving through a system, then the fluid's going to be entering around a point and leaving around a point. That's what we're trying to measure with divergence. It compares how much fluid enters the neighborhood around a point to how much leaves it. If more fluid or flow enters the neighborhood than leaves it, if more fluid or flow enters that neighborhood, the small neighborhood around a point, then leaves it, then divergence is going to be negative. A lot of people confuse that. They go, yeah, well, if we're gaining fluid, divergence should be positive. That's the opposite of the truth. Divergence is how much we're comparing the leaving. Think divergence is diverging, going away. That would give us positive. So if more fluid is collecting in a neighborhood around a point than leaving it, divergence is going to be negative at that point, at P. Think of this as fluid gathering at the point. Let's think of another case. What's the other case? If we're talking here about more fluid enters than leaves it, we're getting negative divergence. We're collecting fluid in that neighborhood. What's another case?
If more is leaving than collecting.
Okay, so if more leaves than enters, or vice versa. What's another case? We're going to do the middle case.
If they're equal.
Equal.
Yeah.
If the same amount of fluid enters as leaves, so these things are equal. So same amount of fluid flow, and the reason why I'm using flow is because we can do things with like charge, like electrical charge, like with wind. So it doesn't have to be a fluid. It just has to be something that's describing a motion of particles within a field. That's what we're talking about. A vector field describes the motion of particles in a field. So if the same amount of fluid or flow is entering this neighborhood around P as leaving it. Might be common sense for it. What do you think? If we have the same amount of fluid, if more fluid enters than leaves, we get negative divergence. We're gathering fluid. If the same amount of fluid leaves as enters, or enters as leaves, they're equal. What do you think about divergence? What would that be?
Zero.
Be zero. It'd say we're not gaining, we're not losing. It's the same all the time. It would be zero at that point. Here's what we say. There's a special word for this. We call this incompressible. It's the vector field will be incompressible at the point. If it happens at all the points, then the vector field itself is said to be incompressible. Does that make sense to you? Incompressible. Well, think about what that means. It means that this one neighborhood, I can't pack more fluid into it. I can't gain anything. I can't lose anything. It's the same all the time. You can't compress it. You can't anti-compress it. It's incompressible. I'm just going to abbreviate incompressible. You cannot compress it. Head nod if you understand the idea of what divergence is starting to do, just a little bit. Now the last one. Well, there's only one more case. If more fluid leaves the system, more fluid leaves the neighborhood around P than enters it. Then divergence will be, put it together, positive. That's saying that we're losing, think of this as losing fluid. Think of this as fluid leaving the point. Well, hopefully that makes sense with the wording. If fluid's leaving the point, it's diverging from the point. That's where we get this whole thing, divergence. That's why when we have fluid leaving the neighborhood around a point, we get divergence. That positive is divergence. That positive is saying we're losing fluid. That positive is saying we're diverging from the point. Head nod if you're okay with that one. If this happens at a point, we call it divergent at that point. If it happens at all the points, we call the vector field divergent. Just like the movie. Exactly the same thing as the movie. Do you know how it ends?
No.
I'm going to ruin it for you. Do the whole spoiler right now. Read the books. Be surprised for an ending. Anyway, let's do a 30-second recap about divergence, then we're going to go on to how to actually find it. I got to show you a new operator. It's something you haven't seen before. It's not hard, but I'm going to make your math a little bit easier to find divergence. Not a hard concept, trust me. So again, what divergence is, it's the idea of comparing how much fluid or flow in a vector field, if the vector field describes fluid or flow of some particles. It's comparing how much of this fluid or flow enters a neighborhood around a point and how much leaves it. If more enters than leaves, divergence is negative. If the same amount enters as leaves, it's incompressible. Divergence is zero. If more leaves than enters, divergence is positive. It's diverging, we get a divergent system. Show of hands if you understand the concept there. Now, how to find it? So, when we're talking about divergence, well, naturally, we're going to have a vector field. So for some vector field, let's call it big F, of x, y, and z. By the way, for the rest of vector fields, we have three variables. Even if we can plot them on a 2D plane, we have three, meaning it's just like a 3D image of this representation that's climbing forever. Okay, we look down, it all look flat because the vectors aren't changing with respect to z, but we always write the three variables. From now on, that's what we're going to have for vector fields. So for this vector field, and I want you to think of the vector field like this. We had this last time. We said, you know what vector fields are? They're this function that we have a function that gives us the x component, a different function that gives us the y component, and a different function that gives us the k component. And when I plug in a point, it runs through the functions. It gives me a specific vector at every point on an R2 or R3 system. Let's look at that. Does this make sense to you that that's a vector field?
Yes.
You're going to have some functions of x, y, and z, x, y, and z, x, y, and z. It doesn't just have to be x's, y's, and z's. X, Y, and Z in all three spots. You plug in a point, gives you an X component, a Y component, a Z component. You put it together, gives you one specific vector at one specific point. And we learned last time that the vector has its initial point at that point. And then we use the X, Y, and Z components to tell us where it goes and how far. And none of you are okay with that one. Now I have to introduce something new to you. So given a vector field, something that gives me a vector at every point on a system. And given this, that looks weird. That looks familiar, but that looks weird. What is that? How do you say that? It's not a gradient. Del. It's the operator that gave us the gradient. What it is was a partial derivative with respect to x, and that was the I component. A partial derivative with respect to y, and that was the j component. I'm going to run out of space, of course. And then lastly, we had this partial derivative with respect to z, and that was the k component. Can you verify that's the way that we sort of found the gradient? It's just that we did it with the function. We said del of f. It was an operator onto f. We took a partial derivative with respect to x, put it I. Partial with respect to y, put it j. Partial to z, put it k, and that's how we found our gradient. Head down if you're okay with that one. Okay, so here's what divergence of f is calculated as. We say divergence of the vector field. Here's what it does. Takes del dot. Do you remember anything about dot products? Yeah. Takes del dot. Isn't that just the same thing as the gradient? The answer is no. No, because the gradient works with just one function. That's what the gradient does. The gradient says take this del f. It says take the partial of the same function 3 different times. This does not do that. What this does, this runs through the partial derivative. Well, think about it. What do dot products do? Firstly, they work with vectors. Do you have a vector?
Yes.
It's a vector operator. I need to make a point of this. This is not a function. It's an operator. It just tells you what to do. It's just we use the dot to show us what to do. So what this would do, please watch carefully. Please watch. This is just a really nice way to remember the next thing. What del dot f, the vector field, does, it says, hey, here's an I component. There's an I component. Remember that dots multiply the I components. Well, now it's an operator of the I component. Here's a j, here's a j. Operator of the j component. Here's a k, here's a k. Operator of the k component. So what this does, it takes the partial derivative of p with respect to x. That's very convenient because the x component gets an x derivative. Does that make sense? Plus, what do you think the next one's going to be? Partial of what?
Partial of q.
Q. That's what dot product would do. It'd say, hey, first ones, second ones, third ones, all added. Partial q with respect to what?
Y.
Good. And then partial with respect to?
Z.
Perfect. That is how you calculate divergence of the vector field right there. Is it hard? Not really, but you got to have an operator that says partial derivatives x, y, z respectively with the functions x component, y component, z component respectively. Notice something right now. That's a vector field. This is like a vector operator. Is this a vector?
No.
Does dot product ever give you a vector?
No.
This is a scalar measurement. It's measuring something that's going to be positive, negative, or zero. That's all it's doing. It's just telling you what's happening at a point on a vector field, whether it's gaining fluid, losing fluid, or neither. That's all it's doing. Show of hands if you feel okay with that one. Make a little side note, this is not a vector. This is a scalar measurement. It can't be a vector. It's coming from a dot product. Scalar, at most, it's a scalar function that you would plug in numbers to. That's at most what it is. Okay, for real, show of hands if you feel okay with all this, because I'm going to start erasing this side. Any comments or questions at all? So if you had to put in your own words, what would you tell me that divergence would measure?
Flow.
Flow?
How much flow fluid of something going into a neighborhood at a point.
Yeah, that's what it would do. Neighborhood.
All
though.
points within that area.
So think smaller. One point, neighborhood around the point, how much fluid is entering compared to how much fluid is leaving. It can be different at different points. If it's the same at all the points, we have certain terms for that. Zero, we call that incompressible, and positive, we call that divergent. That's what I want you to get out of this for right now. Are you guys okay with it? Our examples are going to go quite quickly, so I want to make sure the fundamentals are there before we do them. Yeah.
So would this be a scalar of one of the singular vectors in a neighborhood, or all the vectors within a specific neighborhood? Or can it be both?
Think super small. Think like a point and a teeny little neighborhood around it that doesn't include any other points. How much? And I'll draw some for you, okay? Let me. How about you ask that question in just a little while? Because we're going to draw some. We're going to look at how these would actually work. But the idea is there's going to be some vectors entering this point to the neighborhood around it and leaving this, and we're going to compare what it's doing. Are there more entering, leaving, more leaving than entering, or the same? The second one's called the curl. What the curl does, it measures the tendency of the fluid or the flow to rotate within the neighborhood of a point. So is it spinning? Is it curling around in there? That's what curl measures. So we're going to write this one down. This is the measurement of the tendency for the fluid or the flow to rotate in a vector field around a point, in the neighborhood of around a point. You know what? A lot of people think of it this way. It's a really good way to think about it. I want you to think of this. So think about this flow, this flat fluid, whatever, air, I don't care. And then what I want you to do is I want you to stick a paddle, like one of those water wheels, vertically right through that flow. So these are all 3D, right? So even if we have this flat surface, we go three-dimensional. So if we had this fluid surface and wind was blowing across it, or the water was moving, or whatever's going on, and we stuck this paddle straight up in the air, would the paddle spin? It depends. That's what curl talks about, is the tendency for, at that one point, whether the paddle is going to spin this way, or not spin at all, be completely static. Does that make sense? That's what the curl measures. So if you think about like that paddle, that water wheel that's parallel to the z-axis, the curl would measure how much the paddle spins. That's pretty much what we're talking about. Now, of course, we got to think about what the curl is going to do. What the measurements mean, just like we thought about for divergence. So here's our notes. curl is positive, if we do this thing that we're about to do, this measurement, and we get that the curl is positive at a point, what's happening is that fluid or the flow or the paddle, if you want to think the paddle, would spin. Well, let's think about motion for a second. If we have something that's thinking think positively and think about angles. If we have positive angular motion, that would be spinning counterclockwise, and that's what this does as well. We'll talk about why in a little bit, but this is going to be counterclockwise rotation, if you will. So if our curl is positive at a point, then the fluid or the flow or the paddle would spin counterclockwise. Kind of like just angular motion. When we go counterclockwise, it counts for positive angular movement, or positive angular movement is counterclockwise. Same sort of idea, kind of for a slightly different reason. We'll talk about why, but let's get this down first. Hey, what would happen if curl is negative? What do you think?
Clockwise.
Yeah. Curl negative point, we get clockwise rotation. That's the only thing that could happen. So we could have this fluid or flow that's spinning counterclockwise or clockwise, or we could have what? Imagine a body of water with no flow, no wind, no nothing. Or even this. Imagine this little paddle in the wheel, in the water, but the wind or the water is flowing at equal rates, perfectly perpendicular to those paddles. Is it going to spin? Only if one's stronger than the other. Only if one side's stronger than the other. So this would have no rotation if the curl is 0. And all of these things occur at the point. At P. At P. The only one that has a special name is this last one. If we have no rotation at a point, if the curl is 0 at a point, we call that irrotational. It just means it's not rotating. If it happens at all the points of a vector field, then the whole entire vector field is called irrotational. You guys get the verbiage here? That's pretty much it as far as the two things that we measure in vector fields. We have divergence and we got curl. Right now, by a show of hands, do you understand what the idea of divergence means? Yes, no. You guys over here? Yes, no. How about the curl? Do you guys get that idea? What's curl have to do with in your own words? Spinniness. Yeah, spinniness. It's a good word, right? Positive curl means that you're rotating, and negative and 0. You're irrotational. That's exactly right. That's what it is. Now, how do we find it? If I leave this on the board, you guys, I don't really want to rewrite it. I'm going to use these same two things. You're going to find something kind of interesting. Divergence is a dot product of the vector field, the function gives you the vector field, and the operator, del. It's telling you what to do. The curl of a vector field. I thought something was wrong. People with the wrong paper. I'm like, we're not that far. Goodness. Same operator, same function that's giving you a vector field. What do you think's going to go in the middle of the cross product? That's right. This is why we get the rotation idea. This is why when we do a cross product, because we deal with the right-hand coordinate system. If we get a positive, positive coordinate system says we're going up. If we get positive, we're rotating counterclockwise. If we're rotating clockwise, it's negative, so negative gives counterclockwise rotation. 0 would give us no rotation at all. Does that make sense? So, oh my gosh, how in the world would you do, what's a cross product of this thing would take this crossed with this. Do you remember how to do cross product? It was a while, it's been a while, right? We did a little bit of it, but this would give us this. What's the first things you put when you actually do the cross product of two things that are stemming from vectors? What do you put? Before that, like all the way on the top, what do you put up there? Then you put the first one, then the second one. So even though it seems a little weird, we're going to put this, this, and this. And remember, it's an operator. It's just telling you what to do. So when we do curl F, and we're doing the del cross F, we're doing a partial with respect to X, a partial with respect to Y, and a partial with respect to Z with whatever those guys hit. That's what we're doing. What's going to go down here?
Q and R.
We don't need the I's, J's, and K's here because this takes care of the I's, J's, and K's. Let's see if you can see where these pieces go. Do you guys understand how to get from here to here, given that these are the same two functions we're working with? Head nod if you can. I don't want to lose you now. So here we go. Hey, respect to X, respect to Y, respect to Z, P, Q, R, how it works. I'm not going to write the whole thing out. We're going to do a couple examples here in a little bit. Remember covering up the all but the I? When you do that across this, you take the partial derivative of R with respect to Y, subtract the partial derivative of Q with respect to Z. So whatever you're touching the operator with, that's the thing you take the partial derivative of with respect to whatever variable that says. Are you sure you're okay with it? Do you guys understand the concept of divergence and the concept of curl? Yeah or no? You want to try a couple examples here real fast? Okay, let's do it. Vector field, yes, no, what do you think?
Yes.
Absolutely. What's it look like? 2D or 3D?
2D from above.
They're all 3D. It's a trick question. They're all 3D. All of them from now on. We're always going to have 3D. But sometimes when we only get a few components, we can pretend like we're looking at it from the top and just draw the vector field on the XY plane. Does that make sense to you? That's what we're going to do. So if I were to draw this, the only reason I'm doing it is so you get a good picture of it. Do you need to draw the picture to do divergence and curl? No, it's super easy. It's really easy. But I want to show you why it's working this way. So if I were to do this, to draw this, I'm going to draw just the X and the Y axes, and we're going to be looking down from the top. Like the Z axis doing this, but look, there's no Z component. It's not changing according to the Z axis. All this is doing is saying this. At every single point, you take your X value, you make it negative, and that is your Y component. Do you guys see it? So these are going to be constant vertically. So if I plugged in like 1 anything, it's going to give me negative 1j. Do you guys see that? So I'd have a vector starting at any point, traveling negative along the y-axis, whatever this number is unit-wise. So 1, 1, 1, 1. and it's going downward because it's negative of whatever number I'm plugging in. What's this side going to look? Is it going to be going down or going up? What do you think? It's take a negative. Oh, negative is a positive, but it's still going along the y-axis. It's still constant for that vertical line, if you will. So here we'd have up, but still 1 unit. Show of hands if that makes sense to you. How long are these vectors going to be?
2 minutes.
Oops, wrong way. Makes sense to you? These ones? But there's still going to be negative, or whatever the x value is, in the y direction. So let's take 3, make it negative. Negative 3. What direction? Negative 3 in the y direction, stemming from whatever point you're plugging in. It doesn't matter. These are all 3 units long in the y direction from every point. And over here we have the reverse. Okay, are you guys okay with that idea? Head nod if you are. Now, this can be a really blown up picture of this vector field. Let's make this a minute scale. So if I put just a random point up there, so let's talk about this point. And let's take a neighborhood around that point. That's a really big neighborhood, but it's going to give you a good picture. I explode the view. I want you to look at what's happening. True or false? All the vectors are constant vertically.
Yes.
True or false? All the vectors are constant horizontally. No. Vertically, the one, now look, this is important for you guys to get, okay? I need you to get the concept. This is going to solidify what divergence and curl mean in your head, so pay attention here. Whatever vector enters up here, the same size vector is going to leave down there. True or false?
True.
Whatever vector enters up here, the same size vector is going to enter right below it because it's constant vertically down there. Yes, no? And over here, bigger vectors, but they're the same size leaving. So every vector that enters has the same size vector leaving. Do you guys get it? Tell me about divergence. What do you think? Because the vectors are constant vertically, tell me about something, tell me about the amount of fluid entering versus leaving. Is it greater, the same, or lesser? Same. Same entering, same leaving, same entering, same leaving, same entering, same leaving. Divergence will be 0. It's going to be 0. Now, let's prove it. Let's prove it. What I want right now, I left it on the board for a reason. Let's calculate the divergence. Again, you don't got to draw the picture. I'm just trying to draw the picture for you and taking 5 minutes to do it so that you understand what we're about to get out of this. That visually you go, hey, you know what? The same amount of fluid entering as leaving means our divergence should be 0. If it's not, we've made a mistake either thought process-wise or math process-wise. Can we find the divergence of F? Given that I've given you a very simple vector field, and that's my operator. Remember, the divergence of F is del dot F. That means that we're going to take you tell me, the partial derivative of what? With respect to what? This says take the partial derivative of the x component with respect to x. Do we have an x component up there? Listen, a lot of people get confused. They go, dude, you got an x! That's an x component! What's going to tell you have an x component? I would. And the y component would be dictated by the j. Be careful on this stuff. What this really says to do is take the partial derivative with respect to x of the x component. There is no spoon. Okay, there is no I, there is no x component. It's 0. The x component is 0. Put that up there with the x so that you would see this. Don't just confuse x's with x component. That's not what's happening. Plus, okay, the next one is relevant. What's the next one? Partial derivative with respect to what, please? I want to write them out for right now so that we see where this stuff is coming from. The partial derivative of the y component. What's the y component?
J.
The J, okay, the J is going to give us the Y component.
Yeah.
Negative.
That is the Y component. It doesn't need to involve the I's or J's or K's. It's just the coefficients of those things. So the Y component is negative X. That's the Y component. We haven't taken the derivative yet. Are you with me? The last one says take the partial with respect to Z of the Z component. You tell me right now, hey, what's the Z component? Is there one? The math for there's not one is 0. Let's see if it makes sense. If this one makes sense, the rest of them are going to be golden, okay? Do you guys understand why we have a 0 here and a 0 here? Head nod if you do. There is no I, therefore there's no X component. There is no K, therefore there's no Z component. The Y component is the piece that's associated, the function that's associated with the J. That's the Y component. So basically, we take partial derivatives x, y, z with the x, y, z components. It's very straightforward. We just got to do the math okay. What's the, well, do I need to ask? 0. What's the partial derivative of negative x with respect to y?
0.
Hey, what's that mean? What's that mean? Because this happens at every point, not a specific point. This was every point. Tell me something about the vector field considering that this happens at every single point. The divergence is 0 tells you that the vector field is... That's right, incompressible. That's what that means. The same amount of fluid for this entire vector field is leaving a neighborhood as entering for all points in that vector field. And this is also 3D. I know we drew it 2D, except there's not a K, no Z component. This is happening. If you look down at the top, all the vectors would be identical looking down from the top. They matched up, just one on top of another. It's happening at every single point in a 3D vector field. Does it make sense? Is this kind of cool, though? To me, it's pretty cool. It's putting me in a better mood. So, yes.
What do you mathematicians use that?
A lot we use this for. And that's the entire chapter, is what I get to show you that we use it for. So we're going to use it for a lot of things. I'm going to answer that question, what we use this for, as we continue through 15, 3, 4, 5, 6, 7, 8, and 9. Okay? All right. So stick with it for the next, it's your life. What's the other measurement? Come on. What's the other measurement? We got to talk about the curl. Now, I want you to look at the picture again. Same picture, same vector field. Think of what's happening. Here's my point. Here's the point. What would happen here? Would this rotate? Would the fluid rotate around the point? If so, how would it rotate? Do you think it's going to rotate?
Yes. Negative.
Are the vectors... Now, the idea of rotation is, are the vectors stronger? Divergence was this. Are the vectors stronger on the top versus the bottom? That was divergence. They were equal. Rotation is, are the vectors stronger on the left versus the right, or right versus the left? If that's the case, you will have rotation. Are the vectors stronger on the right or the left?
Yes.
Which one? They're stronger here. So yeah, fluid's both entering, but this is like, oh, way strong. It's like just a little strong. It's going to rotate, and it's going to rotate this direction. Do you guys see what I'm talking about? The curl should be negative. Should be negative. Clockwise rotation, negative curl. So here, we're trying to get the curl F is going to be negative. Let's find it. Did you guys catch that the vectors on the right side of the point, if I draw a vertical dotted line, right side of the neighborhood are stronger than the vectors on the left-hand side. It's going to push it more this way. So even though we have vectors both sides, the stronger ones are going to dictate what happens to the fluid around that point. Let's find the curl. Cross product versus dot product. Create for yourself the I, the J, the K. You tell me, please, right-siders, you guys help me out. What's supposed to go here, here, and here? Pretty much every time you do a curl, what's supposed to go there? The function or the operator?
The operator.
So we need this, and that. Head now that you're with me. Left-siders, you get this one. What goes down here specifically from the function that's giving me my vector field? What goes right here? How much? What right here should be the x component of that vector field? Is there an x? Is there a function that's giving us an x component? So what goes there?
0.
What goes here? What goes here? When you get used to it, you're gonna do this and this right next to each other and go, hey, the same stuff I put here, here, and here, that is my x, y, and z components, that also goes here, here, here. It's the same stuff. Are you with me? Now you're gonna get the opportunity to do this by yourself in a little while, but I'm gonna do this one for you. Here's how to work this. Just be very careful. Of course, your signs can get all screwy, and make sure that when you're doing partial derivatives, man, you look at what variable you're taking a derivative with respect to. So here we cover this up. Hey, what's the partial derivative of 0 with respect to y?
0.
What's the partial derivative of x, negative x, with respect to z?
0.
0. I know I'm writing it 0, but I want to see where I want you to see where the stuff is coming from, and now that you're with me. Next up, what's the next sign I write no matter what all the time? What is it? Yeah, you're subtracting here. So I cover this up. Hey, what's the partial derivative of 0 with respect to x, ladies and gentlemen?
0.
Minus the partial derivative of 0 with respect to z.
0.
That's our j component. Notice that the curl, it's a cross product. It's going to give you a vector if it exists. It will be a vector. This was a scalar. This thing is a vector. It's showing you the direction and the magnitude of spin. That's what's happening here. And then lastly, the important one for us, we're going to get something out of this. We cover this up. We go, hey, what's the partial derivative of negative x with respect to x? That matters. What is it? Minus the partial derivative of 0 with respect to y is 0. And that's our k component. Let's do all the work. 0, 0, how much is it? Negative k. The curl is going to be a vector. A cross product always gives you a vector. It tells you the direction and the rotation of the fluid around that point, of the paddle. That's what it's telling you. This is why we keep all our vector fields 3D, because if you did 2D, you go, K? What the K is that? That won't make any sense at all. So here's what's happening. If we're looking at the top of this, right, and this is the XY plane, and there's a paddle at these points. The paddle, and we're straight down there. The way that this paddle is rotating says, okay, well, negative. What's that mean? Negative means right hand rule. You go that's rotating into the board negatively. So that paddle is rotating this way, almost like a torque concept. It's rotating. That negative says that we're rotating clockwise. That's what's happening here. It's a vector that's into the board and rotating clockwise. That's the idea. Should fans feel okay with that idea? So this rotation it is less than 0. That's the idea for us. It's kind of exciting. Let's go ahead. Let's do one more. I'm going to draw one more picture for you so you can get one last concept of this. And then honestly, the rest of it's just going to kind of be plug and chug with some harder problems that I can't draw pictures for. So this last one I can, though. Oh man, what's that look like? 15.1. We actually did this one. If you remember what this is, these are vectors that have magnitude of 1. They're all unit vectors. They're all pointing away from the origin is what this looks like. So if you were to draw it, we already did, but maybe a better way to draw this would be, well, you know what? If they're all unit vectors, and they're radiating from the origin with a magnitude of 1, then all of these vectors are going to do this out from the origin, and they would hit a unit circle. Yeah, I gotta draw them. Oh, that's kind of pretty too. I gotta draw my circles as dotted. That looks fantastic. That's the best circle I've ever drawn. Not even a real circle. Crap. How come I can't draw a real circle, but dotted circle is just fine? Shoot. Just draw them dotted. And then out here, we can have the same thing. They'd be unit vectors radiating directly from the origin. I'm not going to draw the whole thing. Hopefully you get the idea. It looks something like that. Show of hands feel all right with this one. Now, I'm going to pick a random point. Right there. Call that P. Let's make a symmetric neighborhood around this point. Little circle. And now I'm going to explode that circle. If this is a symmetric circle around that point, then what's going to happen with this? If this is the origin, we're going to get this little V shape. Are you guys getting the picture there? Now these vectors are all stemming from the direction of the origin, headed directly away from that. No matter where they are, they're going directly away. So no matter where I draw this point, I'm going to have this kind of these rays heading off, being tangent to this neighborhood. And what's going to happen is that I'm going to have vectors hitting the inside of this neighborhood and leaving the outside. But here's the point, the major point of this. Check it out. If I look at the vectors entering and the vectors leaving, are there more vectors entering than leaving, the same number of vectors entering than leaving, or more vectors leaving than entering? What do you think? Leaving. Look at the arc length. Look at the arc. There's a lot more circle out here. That means that I have these vectors. They're not different lengths, but there's more of them. They're all unit length vectors, but there's more of them. So you tell me, what about divergence? Think back, don't answer before you think about it. Should divergence be positive, negative, or 0? What do you think?
0. Positive.
Are there more vectors leaving than entering than leaving, or the same? More leaving than entering, and we're talking about diverging. We're going to have divergence of F is going to be positive. It's losing fluid. That's what's going to happen. It's going to be greater than 0. Now, I got to tell you, for a lot of this, we're not going to straight up calculate the divergence. We're going to set it up. I'm going to show you what it is. It takes about 10 minutes to actually do the partials, and I don't want to do that, so I'm going to show you what it is. What I want right now, I want you to set up the divergence. Can you please do that? Okay, right-siders, come on, help me out here. What's, I know that I'm going to do partial x, partial y, partial z. I'm going to add them as a dot product. What goes here, please? Is the, what goes here? The I component. Tell me specifically what you mean by that. What is it?
X over.
Okay, so this. What goes here?
The G.
Okay. What goes there? Zero. Perfect. If you do the partials, this is 0. This and this, a lot of similarity happens. You have a little bit of factorization. You multiply through with a square root of x squared plus y squared, do some simplification and add. And what this turns out to be is 1 over the square root of x squared plus y squared. Tell me something about, and this is true, okay? Do the divergence equation, do it on your own. You know partials, right? I know you know partials. Do it on your own. Make sure that you can get down to here. It is algebra, but you're going to have to show that. This is the divergence. Tell me something about the divergence of f. Is this always a certain value? What do you think? Could it possibly be negative?
No.
Is it going to be 0? No? You fail domain if it's 0, because you have 1 divided by, you can't have 0. This is always positive. Divergence is positive. We have more fluid leaving every single point. We were not point specific here, every single point. So more fluid leaves the neighborhood of every single point than enters it. That's called what for the vector field? That's divergent. It's a divergent vector field, for sure. So hence feel okay with that one. Let's talk about curl for a second. Are the vectors on the right side stronger than the vectors on the left side, weaker than the vectors on the left side, or the same as the vectors on the left side?
The same.
They're exactly the same. Tell me something about the curl. What's the curl going to be?
0.
0 at every single point. What do we call that for a vector field that has curl of 0 at every single point? Yeah, that's right, irrotational. So our curl is for sure going to be 0. Now let's set it up. I've already done part of it for you. I have I, J, K. I have partials here for you. Can you finish that off for me, please? And then we're actually going to do the curl of this thing. So left side, you help me out this time. Please tell me what goes right here quickly. Honestly, all I heard was squared, but I'm imagining that's what you said. Is that what you said?
Yes.
Okay. X, yep, right there. Y, right there. 0, right there. We do our. Well, let's figure it out. For the I component. Hey, what's the partial derivative of 0 with respect to y, please?
0.
What's the partial derivative? I love this when this happens. What's the partial derivative with respect to z of all this stuff?
0.
There ain't no z's. Minus sign. In the middle, the partial derivative of 0 with respect to x. That's how these operators work. What is that, please?
0.
Minus the partial derivative of this with respect to z. What is that?
0.
Lastly, this one gets a little nasty, okay? I'm going to do it for you, but we add, you get the partial derivative. I'm going to look weird on the video. Like, whoa, that guy just shrunk, like totally. Don't take steroids, man. Joke, all right? Stunt sugar or caffeine? I don't know which one. Probably both. If I take the partial derivative of, well, I covered that up. Partial derivative of this with respect to x says I have a bring up a 1/2 power negative. I'm going to have a negative 1/2 by nature of that multiplication. I'm going to have a chain rule with respect to x. I'm going to have a y because that's not a variable. And I'm going to have x squared plus y squared to the negative 3/2 power. That's the first thing I would have in this k component. Then I'd have a minus, and I do the partial, so here, we just did. Here, the partial derivative of this with respect to y says, it's the exact same thing. It's just, well, you have a negative 1/2. You have a 2y by the nature of the chain rule. Then you have an x by the nature of that thing's not a variable, it's a constant. Then you have the same exact expression raised to the same exact power, and that's your k component. Are these exactly the same, and are you subtracting them? They are exactly the same, and you're subtracting them. You're going to get 0. Curl 0, curl 0, and we just proved it. Does that make sense? Do you feel confident and comfortable finding divergence and curl of vector fields? Can you do it? Show me. I've given you an easy one. I'm going to give you just a little bit of time. Don't draw pictures. I don't care. I just showed you these for your convenience, so you can actually see what's happening. That's important that you see it. Now I want you to find divergence and curl, purely mathematical, and then write out a word at the end of each one of these and say what it means for the vector field. Please start that. If you get done really fast, if you're a quick worker, try the next one. We're going to work through it together. But if you want just a slightly different take on the problem, try this. Only reason why we're not drawing these is because they have z components. They get kind of nasty to draw. The other ones, they're all the way, man, same level curve, if you will, of the vector field the whole way along the z-axis. Hey, did you start this? Did you have I given you enough time, or do you need more time? This one over here. You need to look up to know what I'm pointing at. Have you finished this? Okay, take about another 30 seconds if you would. You know, every time I do these, I don't care where you're at in math, I've been doing this for a really long time. Every time I do these, I write it all out. Because it's silly to make little mistakes because you accidentally transposed a function in your head. Does that make sense? Be careful, mathematicians, all right? So here we do partial with respect to x of the first thing. I'm writing all of it out every single time. Even if I do some of the work in my head later, that's okay, but write it all out. Then I'm doing partial with respect to y of the next component. And lastly, partial with respect to z of the last component. Should I put i's, j's, and k's for divergence? It's not a vector. It's a scalar measurement of how much fluid's entering compared to how much fluid's leaving the system around a point. What goes here, please? And here? And here. And in the easiest partial derivatives I think I've ever, well, besides zeros, I guess. What's the partial derivative of every single one of these?
0.
It's all 0. Now, I said, now, give me a word for this. What's that mean as far as, because this happens at every single point. We did not plug in a point here. It happens all the time. Tell me something about the vector field. What's it called? Perfect. This would be an incompressible vector field, and incompressible at each point. Now for the curl. Curl's just slightly more involved, not huge. It's just as a cross product involves a little bit more work, but you also have to show a little bit more work on it. Just in the setup, really. I always like doing divergence first. You don't have to, but I like it because it already organizes my thoughts for me and put them in the same exact order. And we started out. The partial derivative of, by the way, did you get it in this order at least this far? Show of hands if you did. Make sure you got that. Cool. Partial derivative of xy with respect to y. What's that? Minus the partial derivative of, so we actually have to do some stuff here. Partial derivative of xz with respect to z. What's that give us? And this, whatever it is going to be the I component. Next time we always put, when we're doing this method, we put a minus and we go, okay, let's start working on the j. Partial derivative of xy with respect to x gives us, and then minus partial derivative of yz with respect to z is also y, and that's the j component. Last one plus partial derivative here gives us z, partial derivative here gives us z, and we subtract them. What is it?
0, 0.
Not only 0, it's a 0 vector. That's what it says. 0 vector. It's not up, it's not down, it has no direction, and there's no magnitude. There's no spin. What do you call that again?
Irritation.
Incompressible irrotational vector field. Are you still with it? We're almost done. There's only one and kind of a half more examples I need to show you, and then we're going to finish up our lesson and we'll be done with this thing. So the last one before the last one. Could you find, I asked you to do part of it, could you find divergence and curl at a point? You can if you don't get 0. If you get a function to actually, or a number, if you get a function to actually plug stuff into, well, then you don't have something that's necessarily irrotational or incompressible or always positive or always negative. You might have something that changes at certain points, and that's what this one's going to do. So I'll show you how to work on it. Let's do divergence first. I do want your help with it, please. Tell me the first thing that I should have. Don't give me answers, give me setup.
Partial derivative with respect to x.
Of
xy.
perfect. And then
Partial with respect to y of xz.
perfect.
And partial with respect to z. xy squared.
Fantastic. If you did it on your own, did you set it up like that? Then when we do the divergence, we have, well, this is going to give us y. This gives us
2x.
Hey, is the divergence of the vector field always positive, always negative, or does it depend? It really depends on the point you plug in. Well, that's what I'm asking you for here. So we can't say a blanket statement about every point here. We can just say a statement about certain points here. So whenever you get this, you go, man, it's asking for at a point. It's not a big deal. Do the exact same thing and then plug in the point. So if we want to find divergence at that point, and just match up the right numbers with the right variables, you got it nailed. What's our x value that we should be plugging in? And our y value?
2.
And our z value. So divergence of f when evaluated at -1, 2, 1 should be 2 plus 2 times -1 times 2 times 1. Looks like it's
-2.
yeah, -2. Now, what's it mean? What's it mean about that? About the vector field at that point? Are we gaining fluid at that point? Are we stagnant at that point? Or are we losing fluid at that point? We're gaining fluid at that point. The divergence is negative. The more that it's negative, the more fluid that we're gaining. Does that make sense? That's the idea here. Let's do the curl and then we'll be all done with this section. I get well, yeah, probably just do one slight problem after this. So curl, same thing as always. We're doing a cross product. We have I, J, K. Partials with respect to X and Y and Z. And then we have the same exact functions that are given us our X component, our Y component, and our Z component. We should have a little bit more work to do here because it's more involved. We're not going to get a whole bunch of zeros. So first one, can you help me with it? If we start here, what do we get first? Come on, just shout it out at me. I need to know quick.
X squared.
Minus what?
X.
And then what?
I.
Perfect. You got to have the I. Then what?
Minus.
Love the minus. Then we're going to have something else. Okay, well, let's cover this up. What's the next thing I would have, please?
YZ squared.
Yeah.
Minus
Oh, 0. And that's
Yeah.
J. Plus the last one says we're going to get
Z.
Z minus
X.
K. Oh man, okay. Well, is that always 0? Does it depend?
Yes.
What's it depend on? Plug in the point. So let's evaluate this vector. Notice it's a vector. Curl F always gives you a vector. Evaluate this vector at the point. So I'm going to rewrite it just a little bit. And let's evaluate this at that specific point. Well, if that's the case, it looks like we're going to have, let's see, negative 1 times 1 squared minus negative 1 I. Can you see that we're going to get 0 for the I component? Hello, yes, no?
Yes.
Okay. Next up, we have a minus. We have, well, 2 times 1 squared. That's 2j. And then we have this 1 minus negative 1. That's 2k. So our curl is negative 2j plus 2k. You okay with it? What? Now, this is interesting. We don't have something that's going directly into the board parallel to the z-axis. I'm going to make a couple notes, and this is the only reason why we did this example, so you would see what this actually means. Are you ready for it? No? Yes? No?
Yes.
Here's some notes on curl. The maximum, and this should be logical, the maximum rate of rotation will be the length of the curl vector, the magnitude of the curl. That would be the maximum rotation. Maximum rotation, it's got to be equal to the magnitude of the curl F at a point. So at this point, at this one specific point that you plugged in, the maximum rotation would be this. Never going to find magnitude? Tell me how you find magnitude.
Square
them, add them, square root. Would be 2 root 2. That would be the maximum rate of rotation around that particular point. You guys okay on where that comes from? Now, last thing. the only time, do you remember talking about the paddle, how the paddle spins? Remember that? So imagine it perpendicular to the vector field. Well, here's what I want to tell you. The maximum rate of rotation only happens if the paddle is parallel to whatever that vector is. Maximum rate of anytime if the rotation's along that vector and you have a paddle that's like this, it's taken away from that rotation. It's not affecting it as much as it could be. Does that make sense? So maximum rotation only happens when the paddle is parallel to the curl vector. Otherwise, we're losing rotation. So when everything's all said and done, do you feel like you had a good concept of what divergence means, the gaining versus losing? Do you feel a good concept of what curl does? What's it measure? Maximum rotation happens what? Where? How much? Magnitude of, but only if the paddle is parallel to that curl. Only if it's in the same direction. That way we obtain the most spin, most bang for our buck. Okay? Question?
Which way would this be curling then? Because it's negative 2j.
You got to figure out where that vector's going. So if we have negative 2j plus 2k, so that's negative 2 in the y direction plus 2 in the z direction. That's the direction it's curling, positive around that. So counterclockwise around that particular vector of a magnitude that if our paddles belong that direction. Does that make sense?
Mm-hmm.
Okay, we just finished our section. We're going to take a little break before our next one.